So, hello everyone. Let me show you demo for my project tenor. Let us just shift to VS Code to show you something. Here you can see that we have two wallets on Monad testnet, both with real Cleanverse credentials. I am sending each one a real A token that I issued through Cleanverse. First wallet, our registry says live, 34 million seconds remaining. Transfer succeeds, and you can even see the hash here. Second wallet, our registry says is live, false. Look at the expiration timestamp. That's yesterday afternoon. Now look at what Cleanverse own API says about the exact same wallet. Status 1, active. You can see the transaction also that it is reverted. It shows execution reverted, unknown custom error. You can see in this table that there are two wallets, both report active. One transfer works while the other does not. The status field cannot tell them apart. The credential expired and nothing in the API ever said so. Now, let us go back to the site and let me tell you the problem which we have solved. Let us just go here. And yeah, so every compliance check in this ecosystem answers one question. Is this trade legal right now? That works for a spot transfer, where right now and settlement are the same moment. It breaks the instant an instrument has a term. A forward struck today, settling in 30 days. Buyer's credential expires in 15. Legal when it struck. Illegal when it settles. Nobody prices that gap. And when it happens, the standard response is to freeze the position. It protects the protocol and leaves the counterparty who did nothing wrong holding locked capital with no resolution and no compensation. Clearinghouses solved this decades ago. Initial margin isn't sized for the current instant. It covers the closeout window because that's where the risk actually lives. That idea has never been ported to credential risk. Let us know. Let us scroll down so that we already know the problem. Let me show the credential inspector. We can see here that if I load a live credential, it will show me that yeah, it is active. Let me just load an expired credential as well. It is showing me active and expired. And to show you that it works for all addresses, let me just copy one of the address from my notepad and check for it. Yeah, it is active also. So you can see that this reads the deployed registry live from the browser. No backend. Here's the contradiction rendered in this case, where the API says it is active and the credential is expired. And I also showed you that it can take any address, not the preloaded ones. It is live read and a deployed contract. Now let us go to the mechanism and the pricing section. You can see in these 5 steps here that the both parties are verified at open. The gap gets priced, not gated. Escrow takes all three legs atomically: the note, the funds, and the bond. A re-verification checkpoint before settlement. And finally, a deterministic outcome: settled, unwound for expiry or unwound for freeze. It is never ambiguous. You can see the bond pricing formula as well here, which is used for the bond calculation. If I scroll further, you can see the bond calculator is here. I can just tweak in some values. I can just have it something like this. I can have it here like this. And I can change even this to 30 days or something like this. You can see that the bond scales with the exposure gap in days, discounted for deeper verification, capped at 20%. Those parameters are illustrative. A real issuer would calibrate them against actual loss data. The mechanism is the contribution, not the numbers. So if we scroll further, let me show you the real executed runs on Monad testnet. Every line from now here has a transaction hash. You can see that there are 3 beats, and on beat 04 we have a pricing simulator. So this is the beat 01, where you can see the executed trace and the attested on-chain. I can just open this and you will see that it is a real transaction on Monad testnet. You can see it as success. Let me just go to beat 02 because that's where all of the executed runs are there. You can see that trade is opened here and there are 1000 TUSD, bond 74 basis points, matching code bond exactly. Now, what happens is that buyer re-verifies before the checkpoint and we detect it properly. A new KYC hash, not a timestamp bump. That's cryptographic proof that re-verification happened. This transaction is also success as you can see. And at the end, the settles clean. Note to buyer, price to seller, bond returned. You can see that even this transaction is working. Yeah, it is success. Now, let us go to beat 03, which is a second trade, where buyer never re-verifies, settlement arrives, unbind buyers, and seller is made whole from the bond. You can see from these two transactions the same thing, that the buyer never re-verifies, settlement arrives, and here in this transaction you can see that unbind buyers and seller is made whole from the bond. So you need to watch the buyer's refund now. The settle Like in this point you can see that the settlement asset is itself credential gated. So the buyer expired, which is the entire reason we are unwinding, cannot receive their own money back. A normal protocol reverts here, and those funds sit behind a failing transfer forever. Tenor credits the claim instead, 0 to 1000. Buyer re-verifies, calls claim, receives every single unit, claimable back to 0. Never confiscated, never stranded. That is the difference between unwinding a trade and freezing someone else's funds. And you can see that it is not a diagram. This is a real transaction on Monad testnet. So yeah, these were the 3 beats. And if we go to beat 04 as well, you can see that there is a pricing simulator also with same 4-point arithmetic. So you can move the inputs and you can see how the curve behaves. and it is clearly marked as a simulation because it does not subvert anything. The runs that actually executed are the three tabs I just show you. You can just have something like you can uh, play around with these to see what actually happens here. Now, like let me also share the findings which I got while building this project. Let us just shift to VS Code once again, and let me just clear this, and I'll run this command. So you can see that on chain, a contract can learn that an address has an A pass. That's all. Everything else reverts. Remaining credential life isn't readable on chain at all. A protocol discovers expiry by reverting. That's why the registry exists. A relay signs the off chain state as an EIP 712 attestation, and the contract mirrors it so duration becomes a number you can price. The second finding which I found was that minimum tier, groups, countries all expressible, but there is no time field. You cannot write requires 30 days remaining, even though expiry is precisely what gets imposed and transferred. And third and the final finding which surprised me was that I transferred my own A token to the settlement desk. It reverted, no A pass. Even though the desk is a fully registered CleanVS validator, compliance pool with rules you can read back from the API. I looked for register A pass on the A pass registry on the access core. Neither implements it. So no escrow, no auction venue, no settlement desk can custody an A token today. That's not something I worked around. It's the reason the settlement asset mirrors A token semantics rather than being one. Let us go back to the site now, and you can see that these four contracts all are on Monad testnet, all verified on Sourcify. 51 tests, including a stateful invariant over 720 randomized calls. Every trade exports an audit pack tied to on-chain hashes. So this was my project. I hope you liked it.